Hi, and welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack! In these episodes, mini optimizations continue. Today, an improvement of 60% by receiving. Actually made tons of changes to the code, but the boost is coming primarily from the receiving optimization. So, let's go. Proguard plus Gradle. The debug code is starting to grow, so I wanted to clean it out using Proguard. Since it's much easier to integrate it using Gradle, that's what I did. However, tilted no performance gain. Still, it's a nice to have feature as now we can be more aggressive with debug and analytics checks. Moved wheels into Siever. I noticed that Siever threads are stuck waiting for the PolyMiner to produce more work. It puzzles me for a while, since the Siever is much slower than the PolyMiner. But then I figured that we have many Sievers and just one PolyMiner, so the resource distribution is not so good. I solved it by taking 97% of the PolyMiner work to the Siever, the wheels generation part. I think it improved the performance by 2 to 3%, not sure. But again, it feels like a really good change, since it makes the bottleneck much more visible. Analytics. I moved the analytics logic from the logger to the new analytics class and added a percentage counting, so it's easy to see what portion of the code takes most of the resources. And finally, receiving. This is where the performance boost is coming from. When checking if x is smooth, we used to try and divide it by all primes in the prime base. Now I made two optimizations. First, I check if x index is in the sieving array is divisible by one of the primes. This way we don't have to work with big integers. Instead, we only compute mod on Java ints. After finding a prime that is divisible by x, I don't divide x by it, but instead build a Java long multiplication and switch to big integer after the long running out of space. So we are working on small values. Finally, when I computed a big integer that it's a product of all the primes in the prime base that divides x, I divide x by it and convert it to long. I then continue factoring that long. So basically with this optimization, we are almost not working with big integers anymore. All is done on ints and logs. Logs. Cool. So let me show you all of those items in the source code. It was pretty intense. I hope you are going to like it. So let's start with the Siever, where all the changes are made. All right. Um, I added a bunch of new checks with that inside the analytics class. So this is the enums that logger used to be, and it have now a group parameter. -1 says there is no group, and 0 says there is a group. So all of those items are going to be calculated together, and a percentage will be calculated for each of them out of the total time of all the zeros. So just one group really for the Siever, because the PolyMiner and the vector extraction and the metric, are running on just one task on their thread. So it's always like 100%. Okay. Yeah. So this is how I found that the queue actually takes time. And this is why I moved the wheels construction, the build wheels, into the Siever. So build wheels, it's the same method that we had in PolyMiner, with one difference, which is the prime mod squares. That before that was a hash map, but since the index of that prime is always the same, I just iterating over the index of the prime mods squares, which are now in array list, and it consistent with all the wheels. So that mapping of mod square index to the prime root is always the same. It's deterministic. And I'm computing it inside the PolyMiner. So it happens here, just going through the primes with the same condition of respecting the minimum prime size and the special case of prime of this 2 prime. And then I just add the mod square. All right, back to the Siever. So those are the wheels. Next, no many changes except the parts of the code that I'm tracking. So there is Siever core, Siever collect, and receive, which is the super cool new optimization. So those two didn't change. They are now just tracked. And for receiving, we're iterating over the wheels and then calling to update smooth, which takes all the bismuths that we found. And then for each bismuth that we found, it looks at the local x minus delta, and then mod the prime should be equal to the starting position. The starting position is what we've been getting here. So I'm modifying the current position as we iterate over the update loop, but the starting position is not changing. It remains the same. It's just being reset each time when we are reusing that wheel for other polynomials. But beside that, it's kept the same. And so we can expect that if the value that correspond to that bismuth data is actually divisible by that prime, then mod prime will should be equal to the starting position. And if that happens, so bismuth data contains the log, local x, and a reminder. Let's talk about the vector now. So the vector is what essentially going to be converted into our bismuth value. And we are constructing it right here by setting the prime index. We're also computing the logs that we already computed. I'll show in a moment why do I need that portion. Actually, it's here. So one is getting to the max long. So that portion of code. We know that this item is divisible by the prime. And now we want to compute the multiplication of those values. So there are two values for it. There is value, which is a long, then big value, which is a big integer. The big integer starts with null. And while it's null, we are working on the long value. When the long value is running out of space, and that we are checking by that condition, if the logs are actually getting bigger than the long max log, which is, where do I set that? In here. Yeah, so it's static, it's set just once, and it's equal to that item, to that number. Okay. So while this condition holds, we're multiplying the prime by the value. Oh, that's another cool thing. So now I'm having an assertions where I'm checking. So if that check fails, then an exception will be thrown with long overflow. So I know that the code. I was running into this problem several times, so I added this check. And otherwise, we just continue build the value, the long value here. Then when that fails, we are computing the big integer. And once we computed it, so it's not null anymore, we are continue to multiply and update it by the value of the prime. Awesome. So this is how we compute the big value and the be smooth. And then, okay, the remainder will be next. So we done this portion. So of the receiving, we updated the Bismuth values. Next, we're iterating over all of those Bismuth lists again. And now what we are doing, we are computing the sieving value by get sieving value. This is similar to what we've been doing before, but now instead of try and extract it and extract the vector out of it, what we are doing, just reusing the vectors that we computed earlier in here, and we are dividing it by the big value. Now the remainder is expected to be smaller than 64 bits, and we convert it to long and use the remainder in here. We then continue and extracting it as part of the vector extraction total. Now let's see how the vector extractor changed. All right, so we are working now with longs instead of ints. First, we are checking if it's a negative value, and then we are applying the -1 vector and making the value positive. Next, we are not using the big integer and get last set bit, but instead there is a cool method in Java, number of trailing zeros, which is implemented using that hack. That gives us the power of 2. This is just checking if the number is divisible by 2 in a slightly more efficient way. Just wanted to be cool about it. I'm not sure if it's really giving a big performance boost, but anyway, this is how we are updating the vector 2, the prime 2 in our vector. Then we're just dividing by the remainder. If it's 0, it will not change the remainder. All right, and now getting rid of the rest of the primes. So we are iterating over the prime base. And if the prime is bigger than the remainder, then we are done. So I don't expect that loop to get until the last prime, but it could be that we missed powers, we missed some of the prime values in our prime base. So we're just iterating over all of it again. Once we find a power, then we dividing the remainder by that prime, and we are using here a flip instead of set, because if it was already set, then we need to undo it. If it wasn't set, then we need to do it. So a flip instead of set. Cool. Now finally, we have two options. Either we found a completely Bismuth value, then we just putting it inside the Bismuth list, or it's a big prime. Now the big prime is a long. I don't know why it was a big integer in the previous implementation, but no big changes in this portion of the code. Except one thing, if you noticed, no longer checking if the value is indeed a prime. So it could be that the reminder is actually a composition of two items, but it would be a rare case. We need to increase the threshold more to allow a sufficient amount of values to be um, to be a multiplication of several primes. Otherwise, most of the time it will be just a prime, and so the check for it is really not necessarily. In the worst case scenario, we will just not find this composition, and if we do, it will still work because we will treat it as one number instead of several. So that gives a huge performance boost. Now let's see if we talked about all the optimizations. So we mentioned analytics, we mentioned receiver, and moving of the wheels. Let me show you what I did for Proguard and Gradle. So now I'm working with a Gradle build system. This is the Gradle build file. The only line that I'm not so proud of, it's that thing. Yeah, a little bit ugly, but I wasn't being able to find a nice way to point out that I'm using OpenJDK 14 for this execution, and I had to hard code it. But I guess it also makes it easy for other people to just remove it and specify their own Java version. Anyway, it allows me to use the optimization task of Proguard, and inside it, let me show you what I have. So it will run the optimization loop 10 times. It will it will change the package name of everything to just that. This is the flag that helps Proguard to perform some additional optimizations by changing the access mode of fields and methods. And then for the optimizations, it turns out that not all of the optimizations are really useful for us, and some of them are bad for performance. So I just choose to whitelist only those optimizations. So everything that removes code is good, as well as inlining methods. And for simplifications, I don't remember, but I think it also had some logic of inlining and removing some variables. I'm only using those optimizations. Then we need to specify an entry point to the system. It's the Quadratic Sieve public static main method, of course. And in here, I'm removing classes. So everything inside the debug package. You need to be very specific about the methods and the class names, so it will not remove unnecessary items. So inside analytics, we are removing those two prime methods. Logger is not making any logs. And I also moved the log progress to logger. Take it away from, I think it was in vector extractor before. So it makes much more sense have it inside the logger. And finally, assert utils. I just started using it. I only use it once so far, but it's a really cool thing. We can debug the code in real time, and once we are running it, we can use just the optimized version of the program. So it also obfuscates the code and makes it much smaller and compact. It has maybe a small effect on performance, but overall it doesn't change much. I think Once we will have more of those asserts, then it will become more meaningful. But meanwhile, it provides a clean output with no debug information at all, and it's really cool. So that move was very fun. All right, so let me show you how the new performance looks like. I created several outputs of the system, and we are now efficiently at 10 seconds for 200 bits. Went down from 70 seconds, so it's quite a boost in the performance. Also, now I would put the resource allocation. Oh no, I think this one was one of more older executions. Maybe in here. Snap! I didn't took the right output. Let me quickly show you what I mean. So now, when we are executing, yeah, it's much more slower now because I'm recording, but let it finish. Oh, it kills my scroller. Yeah, we are factoring 200 bits number. Okay. So what it prints, it's the percentage. How each part of the code, how many percent, what's the percentage allocation for each portion of it. So Siever core takes the most performance now, most resources. It takes 45% of the total sieving time. Receive takes 20%, 19, sorry. Vector extraction takes 8%, and we are no longer stuck in the queue, so 0.14%. So it's really cool. Now we definitely need to focus on optimizing the core part. Let me show you where the core is happening. So, so the core is just that. It's just the update of the logs. So iterating over all of the primes, and for each one of them, we are iterating over the logs array and adding the log weight to the current position. So that takes 40%, that small thing, out of the code takes 40% of the performance and the execution. Yeah, that's funny. Yeah, so next we'll need to see how that can be optimized. And I've been trying to play with magic numbers to see if I can change that 40%, and I didn't find a way to do that. Definitely something to expect during the next episode. All right, if you have any questions, please ask me in the Facebook group or comment below, and the source code will be available at GitHub. Thank you for following me, and see you on the next episode. Bye.